Okay, so thank you very much to the organizers for this seminar series in the middle of summer. And as Sasha said, I tried to give you a really short overview what can be seen mostly in rocks about melt migration, and can we actually recognize the lithosphere-asthenosphere boundary in rifted margins, even though maybe the activity by now is pretty late. It's a fossil lithosphere-asthenosphere boundary, but I will show you that three postulates are necessary to understand the lithosphere-asthenosphere boundary: that melt rock reaction is unavoidable in rifted margins if decompression melting starts at some point. Then, if you have the opportunity to sample rocks, you can find the remnants in exhumed origins, or if you're lucky, you can either drill or dredge it in the oceanic mantle. And finally, maybe we are able to map the fossil lithosphere-asthenosphere boundary. So why is magma so important in rifted margins? And I give you just this overview cartoon from Harkin et al. From Geophysical Journal International, because I think many people can find themselves somehow in the interpretation of these geophysical data. The first model you see is sort of a favorite model for rafters, that in the oceans there could be continental remnants, as indicated here, which might perturb fundamentally the signals of intra-oceanic magnetism. Another favorite model, the number 2 here, we could call this is something for the serpentinizers, because the area of serpentinized peridotite here, as mapped in this figure, is pretty large. The third model, you can see this block here is interpreted as magmatic crust, and this might be in favor of people who like plume models, because that could be related to excessive magmatism at the beginning of rifting. And then the final model is probably something for the politicians among you, because the continental crust and this remnant here is linked by very small continental blocks. And this means a country might claim that up to this point, that is all their own country, with important implications for resources at depth. So if you look what happens if you do decompress the mantle in a rift, basically a simple model you can see on the left is that fertile leusolite would start to rise, and this adiabatic upwelling would produce melt, and higher up in the mantle column, you would finish with depleted leusolites or with harzburgites. And you could then see or ask the question to your mantle rocks, what is actually partial melting, and what is the interaction, what this melt that is produced with the residual mantle could produce in textures. So fertile leusolite maybe have a very complex history, and the melt rock reactions, they are dependent on the thickness of what we call the thermal boundary layer, as indicated here in this figure. On the left side, you could see thermal asthenosphere and thermal lithosphere, and this is separated by the thermal boundary layer, in this case indicated by between 15 and 20 kilometers, designed for a mature mid-ocean ridge. So what's basically happening there is that from an adiabat, you start to cool the melt, and at some point in this thermal boundary layer, and I hope Sonia will address this a little bit more in the second talk, you get all kinds of reactions and changing of your mantle peridotites. So if you look at simple physical models, if you exhume mantle lithosphere, and this is taken from Andy's mice paper, where we do not yet incorporate melting and melt migration, you can see on the left-hand side a model which is run over 15 million years in a temperature depth diagram with the peridotite solidus here. And you do uniform stretching in the mantle and in the crust with a beta factor of about 2. And when you follow a parcel of rock that is close to the moho, you could see with this little arrow here that the rocks would essentially cool during rifting. If you apply a non-uniform stretching model, where you would allow that the stretching factor of the crust is beta equals 2, and delta is the stretching factor of the mantle, equals 5, you get a very different picture over 50 millions of years. If you take again the same rock here, you would see that this part, which was at the mohole, would actually heat during rifting. So it's important whether stretching factors in the mantle crust are the same or not, and this could influence whether the crust gets heated, as postulated in the paper by Smythe, or just cooled if you apply uniform stretching. If you look at the second simple physical model, so for example, when the basalt would rise through the mantle, and I show you a nice little video of a finite difference model produced by Marco Repach at the University of Lausanne, where he simulated a dike which would rise in a temperature gradient between, this is a distance of about 30 kilometers, and he is varying here the melt velocity in the dike for a 5-meter diameter dike, and compares on the right-hand side depths against temperature. And no surprise, the faster your magma is rising, the bigger deviation you see between the white line, which is the geotherm, and the evolution of the dike during rise through these 20 to 30 kilometers from mantle. In the summary, you can see the different profiles, how they deviate from a geothermal gradient. On the right-hand side, you see where this model was applied. Basically, what he wants to show here is that every magma that rises, at some point, it will cool and it needs to crystallize wherever you produce it. If you produce it at 100 kilometers, maybe it gets stuck at 70 kilometers. If you produce it at 40 kilometers, it gets stuck at 10 kilometers. And this will induce melt rock reaction or crystallization in the mantle itself. If it's a grain scale process, then you might find melt rock reaction products in this thermal boundary layer. And if you get a lot of melt accumulated, you might form gabbroic bodies in your mantle lithosphere, more or less close to the surface. If we now compare these thermal boundary layers in these simple sketches, on the upper two diagrams, you can see figures that show a summary of rifted margins towards the ocean-continent transition. And on the lower hand side, you see images from the ultra-slow southwest Indian ridges, which are inspired by Mathilde Canat. Then the area where you get this melt rock reaction is indicated by this orange box. It is clear that on an active ridge system, this would happen at a couple of depths, depending on the thickness of this thermal boundary layer. And in ocean-continent transitions, sometimes these areas get exhumed very close to the surface, or even at the surface, and get serpentinized and covered by sediments. So you could call this here the base of the lithosphere, and then transition to the asthenosphere. You might be able to exhume these areas in a more or less coherent piece and investigate this either by drilling or by looking at remnants that are preserved in origins like the Alps. So how does this rock look like if you make thin sections and try to figure out the textures compared to normal mantle rocks? I compare on this figure two images. One is from the Lanzo-Priodotite in the Alps, and the other one is from the Iberian margin. And what you recognize is that you see clinopyroxenes, one of the important mantle minerals, which is partially replaced by intergrown orthopyroxene and plagioclase. If you go to the Lanzo-Priodotite, you see basically the same textures, that the CPX with the same color, it starts to be partially replaced by plagioclase plus OPX. So this is one textural evidence for a melt rock reaction in a mantle. Other ones are you can replace olivine by orthopyroxene in the shallow mantle lithosphere, or you replace spinel 2 pyroxenes and they will react to olivine and plagioclase. The nice thing about these textures, usually if you analyze them by microprobe or laser ablation, I just show you one example, there is sea trace elements. The clinopyroxene is usually used on mid-ocean ridges to determine the degree of melting if everything happens in the spinel peridotite field. But if the rocks are re-equilibrated or reacted in the plagioclase peridotite stellar field, you see little anomalies, for example, here in europium, either negative or positive ones in clinopyroxene, depending on melt-rock reaction and how much melt was crystallized. And you could also see that the highly incompatible elements on this diagram, now indicated by a light reverse lanthanum and cerium, that they are increasing in the area where we get more melt-rock reaction. So basically, if you sample your mantle rocks on the seafloor, you might be able to detect the signal and the amount of melt-rock reaction in the mantle by analyzing fresh mantle pyroxenes.
You have 10 minutes now.
Okay. So if you try to quantify melt-rock reactions, again, on the left-hand side, you see an example from peridotites from the Alps, in Corsica or Iberia. And on the right-hand side, you see an image from the ultra-slow spreading ridge. Note the difference in freshness of the samples. Then in a recent paper, Birner et al., they postulated here in these rocks, they got about 1% of melt addition to explain geochemistry, while on the left-hand side in the Alps, you could vary between about 5 to 12% of melt addition to explain the geochemistry of the pyroxenes. Of course, this depends what you take as an original depleted mantle signal, but this gives you a flavor of how much melt might be stored in the mantle itself without being mixed. So we can put these different figures into sort of two schematic sketches. Apologize that one is the continent is on the left-hand side and on the upper figure, the continent on the right-hand side. The topmost picture is a reconstruction from results from the Alps, while the lower part indicates sort of a generalized rifted margin like Antarctic Australian margin or Iberia, Newfoundland. And you can find remnants of continental mantle close to the continent, as indicated here by this highly layered proxenite-rich mantle. And you can find infiltrated peridotites with melt rock reaction, exemplified by plagioclase and OPX down here or up here. And usually this area is separated by a more or less wide shear zone, which is indicated here by highly deformed peridotites. And this could be mapped as the lithosphere-asthenosphere boundary in an evolving rift on the alpine side or on the lower figure on an active margin, on a passive margin, sorry. To conclude, the effects of melt migration, as indicated here above the asthenosphere, you get melt rock reaction in this part, and it's mainly emphasized by infiltrated and reactive mantle rocks. The processes that you can study is either melt trapping, thermal erosion, and thinning of the mantle lithosphere. And there is a few consequences for the rifts. Either you could see refertilization of mantle rocks by adding melt that is crystallizing, mostly exhibited by plagioclase. You will change the mantle rheology by weakening by adding the melts. You change the thermal structure. It might be much hotter than you would expect in areas where you get melt migration upward and not just extract the melt to the surface. And this might have an influence on the subsidence history, so you might be able to retard subsidence in sedimentary basin. And just to finalize as a thought experiment, if you have 10% infiltration into a 10 kilometer thick mantle on the left-hand side, this would be infiltration, and you will get a margin that is basically magma poor or non-volcanic. While if you extract all the melt and you form a 1 kilometer thick layer on top of the mantle, you might call this as a volcanic margin. Both have about the same amount of melting. One would be seismically visible with an ice moho, while the other one would probably have a transparent moho. Thanks.
Thanks a lot, There's time for a few questions. If you have one, just put them in the chat.
Yeah.
And while people may type, I ask the first question. I find it amazing how much information we have from Iberia and from the Alps. But could it be that we are a bit biased in our interpretation of what processes play a role by these two locations that are quite close together on the world map? Are there any other places where we could do similar analysis or where it would be interesting to go to?
Okay, so to reply to the first question, yes, of course, we are extremely biased. If you imagine how much rocks from Iberia is drilled compared to the size of the rift, this is a couple of 100 meters. Okay, in the Alps, there is a little bit more, but it's always depending how you reconstruct your margin. And there is chances, for example, I know from a paper last year from the Australia-Antarctica margin, where peridotites that were dredged many, many years ago by the Australians, they were analyzed by Anders McCarty, and they seem to be continental peridotites very close to the continent as you can find in the Alps or in Iberia. The plagioclase peridotite, you find them occasionally also on ridges, but the amount of plagioclase is very different. So I think it's a question of sampling, but they must be there since physics tells us that if melt rises and will not go out at the surface, it will crystallize somewhere in the top part of the lithosphere. So I expect it should be there.
Okay, thank you. There's one question from Sören. Sören, could you please unmute and ask the question yourself?
Yes, hello.
Hello.
Thanks for the great talk. I was wondering about the minimum temperature for these melts to interact, for example, in shear zones. Do you have any idea?
This is a very good question. And again, I guess the minimum, it depends very much on the composition of the melts. So if the composition of the melts contains some water, you could start to crystallize anhydrous minerals and then start to accumulate water, and therefore the temperature could be maybe as low as below about 1050 degrees C, the stability of hornblende. Because in some of these peridotite shear zones, you find hornblende stability, and this would indicate the maximum temperature is about 1050. Okay. If you do classical or thermometry of major elements or with trace elements, the temperatures that you get, they are highly variable depending on the history of the peridotites. Sometimes it's 800 degrees C. So then it's much more difficult to get a decent understanding at what temperature it was active. I prepared a few figures with olivine fabrics from a peridotite from the Alps, where there is a clear indication that where you get a lot of plagioclase, you get a different fabric, which indicates deformation when melt is present. So I would guess it could go down if it's very focused to 1000 degrees, maybe less, but in many cases, maybe higher.
Yeah, thanks. Because I was wondering, for many shear zones where you have ultramyelonites forming, you have somehow temperatures around 800 to 900 degrees.
Yeah.
And there you also have a lot, or often phagocytic amphibole.
Yeah.
And I was wondering if the melt could be as low as this temperatures we see in these ultramyelonites, or
So again, this is a very good comment. The question is always how much subsolidus re-equilibration you get in pyroxenes. And this is unfortunate that, or if we take olivine spinel, the magnesium iron exchange that can go to 700 degrees C, and it might be that the shear zones after the melt is freezing is just continuing to deform because you get already an anisotropy by highly reduced grain size.
Okay, thanks.